So this is where the videos left off that you were supposed to have watched, picking up in the middle of a section here. I'm starting. Please be quiet. So in the videos that you were supposed to have watched, I talked about how to calculate the empirical formula for a compound. That's useful, but oftentimes what we really want is the molecular formula, which we think of as the true formula for the compound. To find that, you need another piece of information. You need the actual molar mass for the compound. That would be determined probably using mass spectrometry. We know that the molecular formula is some multiple of the empirical formula. The empirical formula is like the lowest ratio, the reduced fraction. And the molecular formula is going to be some multiple of that. So empirical formula times n. N is always going to be a positive integer. 1, 2, 3, 4, etc. So to find out what n is, we take the molar mass of the compound. That would have to be given to you in a problem. And we divide it by the empirical formula's molar mass. So it may be a long, involved problem where they make you calculate the empirical formula. Or it may be a shorter problem where you're given the empirical formula. You use that formula, calculate the mass of that formula, and you divide. And this should give you a whole number. So let's do an example. This is a short example. Compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? So we need to find out what the multiplier is from CH to get the actual molecular formula. So we're looking for N. N is going to equal the molar mass divided by the empirical formula mass. Okay, so the molar mass was given to us 78.11 grams per mole. We have the empirical formula. It's CH, and so we calculate the molar mass of that formula. 12.01 for the carbon, 1.008 for the hydrogen, and that adds up to 13.018 grams per mole. So when we take these two numbers, the 78.11, and divide by the 13.018, we should get a nice whole number, 6.0002. If you get a messy looking number, like 6.5 or something, you made a mistake somewhere. You calculated the wrong empirical formula, you calculated the wrong formula mass, something's messed up. Maybe you just divided wrong on your calculator. But these problems are always going to come out nicely. So that is 6. So what this means is the empirical formula of CH, we need to multiply all of the subscripts in that formula by 6. And so the molecular formula is C6H6. Any questions? It's like if you had a box of 10-pound bowling balls, right? Each ball weighs 10 pounds. The box weighs 100 pounds. How many balls are in there? 10. You take 100 pounds, you divide it by the mass of 1, and that tells you how many. So here we're taking the mass of the whole box, the whole formula, dividing by the mass of one piece, and that tells us how many pieces are in the box. Okay. I talked about how we can calculate an empirical formula from experimental data. Combustion analysis is a common technique used to give us such data. This is really useful for organic compounds containing carbon, hydrogen, and oxygen. What happens is the original compound is burned It's combusted, and the products are carbon dioxide and water. And by measuring the masses of the products that are given off, we can find the mass of carbon and hydrogen that were in the original compound. All the carbon goes into CO2. All the hydrogen forms water. If there was oxygen in the original compound, we identify how much of that by subtracting. We know that the total mass has to equal the mass of carbon plus the mass of hydrogen plus the mass of oxygen. Here's an illustration of what a combustion analysis setup might look like. You have a furnace, you put your weighed sample in there, oxygen passes through, it's heated, and it burns. All of the products of the combustion leave the furnace and go through a series of tubes. The first tube contains a substance that absorbs water. So what we do is before the experiment, you weigh this tube, and then during the experiment, the water given off from the combustion goes through the tube and it gets absorbed. When the experiment's over, you weigh the tube again, and the difference in masses gives us the mass of water. So water is absorbed here, carbon dioxide is not. It keeps going. Goes through second tube, here's the carbon dioxide absorber. So this traps all the carbon dioxide, and we can weigh that. If there are other things present in that original sample, those are just going to pass straight through. They won't be absorbed. So let's do a problem here. Upon combustion, a compound containing only carbon and hydrogen produced 1.60 grams of carbon dioxide and 0.819 grams of water. Find the empirical formula of the compound. So to find the empirical formula, what we need are the masses of the elements. We convert the masses to moles of elements, and then we find the ratio. Here, we're giving masses of compounds, and so we need to find out how much carbon is in 1.60 grams of carbon. So we've got grams. How much is in that many grams of carbon dioxide? So we've got grams of carbon dioxide. From that, we can figure out how many moles of carbon dioxide we have. And from moles of carbon dioxide, we can find moles of carbon. We really could just stop there, because when we do the empirical formula, we would take the mass and we would convert it back to moles. So it's easier for a problem like this to just stop here. So that's what I'm going to do on this one. So 1.60 grams of carbon dioxide. We want to convert to moles of carbon dioxide. So we're dividing by grams of carbon dioxide. And then we're going to go to moles of carbon and divide by moles of carbon dioxide. How many moles of carbon are in 1 mole of carbon dioxide? 1. We see that from the formula. CO2, 1 carbon. 1 mole of carbon in 1 mole of CO2. The molar mass we would get by calculating. We would take the mass of carbon, 12.01 plus 2 times the mass of oxygen, which is 32, and we get 44.01 grams. It's 1 mole. Okay, so this gives me a number of moles of carbon, 0.0363. On these problems, the sig figs are going to disappear in the end because we're going to end up with whole numbers. What we want to do is avoid rounding. Rounding can really mess up an answer here. So here's my minimum number of sig figs is 3. Here's my minimum number. This is where some students get into trouble because they forget that the leading zeros aren't significant. And so then they round off too much, and then things get really messed up. I should have 3. I'm going to keep 2 extras just to be safe. And that's moles of carbon. Now I'm going to do a similar process for the water to find moles of hydrogen. So I've got 0.819 grams of water. I'm going to convert that to moles of water, dividing by grams of water. Excuse me. And then moles of hydrogen, dividing by moles of H2O. I know some of you like to do unit conversions kind of in your head and just write what seems to me to be random things down. We're getting into an area now where you really need to be able to write things out like this so that you can go back and see what happened in your calculation so that you don't forget something. How many moles of hydrogen in a mole of water? 2. That's what the subscript tells us. It's 2 to 1. Calculating the mass of water comes out to be 18.016. And so here, I get 0.0909. There's my minimum number of 3 sig figs and 2 extras, and that's moles of hydrogen. The formula, the empirical formula for this compound gives me the ratio of carbon atoms to hydrogen atoms. And so we need to have a ratio of small whole numbers. The way we convert these messy decimals into whole numbers in a ratio is we divide. So we divide by the smallest. This is the smaller one. So I'm going to divide both of them by that smaller one. And that gives me 1 for the carbon. And it gives me 2.5, 009 for the hydrogen. Can I round that to 3? No. It needs to be within 0.1. If it was 0.9, 2.9, I'd let you round it to 3. If it was 2.1, I'd let you round it down to 2, but you can't round 2.5. We need to multiply to get a whole number. This is one place where trial and error works pretty well. Try multiplying by 2, see what happens. 5.002 or 0017. Can I round that to a whole number? Sure. So that's 5. If I multiply the first one, or the hydrogen ratio by 2, I have to multiply the carbon ratio by 2 also. And that gives me the number 2. So these are the coefficients for my elements. So the carbon has a subscript. They're not coefficients, they're subscripts. These are the subscripts for my elements. Carbon has a subscript of 2. Hydrogen has a subscript of 5. That's the empirical formula, C2H5. Any questions? Yes?
Why did you multiply by 2?
Why did I multiply by 2? Good question. This number, 2.5, is not close enough to a whole number, and so I need to multiply it by something to get a whole number. So if I multiply that by 2, I get 5.0017, which is close enough that I can round it. Because what's happening here is that the ratio, or the fraction, if you think of it that way, the fraction is 2 to 5. But when I do it like this, one of them is always going to be 1. If I take 2 and divide by 5, that's 0.4. If I do it the other way around, if I take 5 divided by 2, I get 2.5. So this is the decimal equivalent of 5 halves. And so multiplying by 2 will fix it. If you don't recognize that 0.5 refers to half, that's okay. If 2 doesn't work, try 3. If that doesn't work, try 4. You usually don't have to go any farther. Any other questions? Let's do one that's a little more complicated. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produce 1.6004 grams of CO2 and 0.6551 grams of H2O. Find the empirical formula of the compound. So we need moles of carbon, moles of hydrogen, and moles of oxygen to do ratios and find the subscripts for the empirical formula. Bless you. So what we did before is we took grams of CO2 to moles of CO2 to moles of carbon, and then we stopped. We still need moles of carbon, but in order to find out how much oxygen there is, we need to find the mass of carbon and the mass of hydrogen and subtract them from the original sample's mass. The sample mass equals the mass of carbon plus the mass of oxygen plus the mass of hydrogen. We know 3 of those, we can calculate the 4th one. So we need this value, but then we also need to go on and get grams of carbon. So that's what we're going to do for both hydrogen and oxygen. I'm sorry, both carbon and hydrogen. So there's my grams of CO2. And I'm going to multiply by moles of CO2 per gram. We already did this, so we've got the numbers. Oops, I don't want to cross out the number, just the units. And then the ratio, 1 mole of carbon to 1 mole of CO2. I wrote this out a slightly different way. Yesterday in lecture, I'm going to do it a different way today. 1.6004 divided by 44.01. I'm going to go ahead and write down what that is here. 0.0363. 1, 2, 3, 4, 5. I need 5 sig figs. 1, 2, 3, 4, 5. And then there's 2 extras. That's my moles of carbon. I need that for my empirical formula calculation. I also need to know how many grams of carbon. So I wrote that number down there so that we don't have to do the calculation multiple times. Now we need to convert to grams. Carbon weighs 12.01 grams per mole. So I take that number still in my calculator, multiply by 12.01. And that gives me 0.436 7. Throw in a couple extras. Grams of carbon. So I need the moles of carbon for one thing, and I need the grams of carbon for something else. Now we're going to do a very similar thing for hydrogen in the water. 0.6551 grams of water. And convert to moles of water. And then to moles of hydrogen. I need this number to calculate the empirical formula, so I'm going to write it down. 0.0727. There's my minimum 4 sig figs and 2 extras. Moles of hydrogen. And then I'm going to convert this to grams of hydrogen. By multiplying by the molar mass, 1.008. So my grams are 0.0733060 grams of hydrogen. Any questions yet?
How did you get the
18.016 is the molar mass of water. It's 2 times 1.008 plus 16.
Oh, it's just all of it together.
Yeah. I've just used that one so many times. I remember it. Okay. So we're going to take this mass of carbon and this mass of hydrogen and use those to figure out the mass of oxygen. I'm going to also just create some space up here. So I've got my initial sample was 0.8009 grams. That includes all of the elements. And so I'm going to subtract the mass of carbon, and I'm going to subtract the mass of the hydrogen. That's grams. 0.8009 minus 0.436737 minus 0.073306. And so I get 0.290857 grams of oxygen. I'm taking the total mass of the compound. I'm subtracting the mass from carbon, subtracting the mass from hydrogen. The difference, what's left, must be the mass of the oxygen. We can't use another U-tube to collect the oxygen because we're putting a whole bunch of oxygen into the furnace so that the thing will burn in the first place. So we measure the oxygen by difference. So I'm going to take this mass, and remembering that my ultimate goal is the empirical formula, I need to take this mass of oxygen and convert to grams of oxygen. If we were doing moles, yes. That is grams. Yeah. Sig figs, that would be the last sig fig from that subtraction. Okay, so we're going to take the grams and convert to moles. Grams of oxygen, and then we've got 1 mole of oxygen per 16 grams. So I take that number, divide by 16, and I get 0.0181 786 moles of oxygen. Any questions? So here I have moles of carbon, moles of hydrogen, moles of oxygen. I need to divide each of those by the smallest one. Which one has the smallest number of moles? Oxygen, 0.01, is the smallest. Okay, so the ratio for that one comes out to be 1. There's always going to be 1. There can only be 1. 181,786. So for the carbon, I'm getting a ratio of 1.9993. So that's very nice. And then for the hydrogen, 0.0727242 divided by 0.181786. For the hydrogen, I'm getting a ratio of 4.0005. Can those be rounded to whole numbers? Yeah. So the subscript after the carbon is going to be 2. The subscript after the hydrogen is 4, and the subscript after oxygen is 1. So it's C2H4O. It's the empirical formula. If I was doing that on paper, I would have used a lot more space. It's kind of cramped. Any questions?
How do you know how to put them in order?
How do I know how to put them in order? That's a good question.
It says up there containing only carbon, hydrogen, and oxygen. Do you go by the order they list it?
Yeah, so there's a couple of different ways. I did give you the guideline that for these molecular compounds, we generally put the more metallic one first. And so carbon is to the left of oxygen, and so that's a reason for putting carbon first. You might say, well, what about hydrogen? Hydrogen's way over there with the metals. Well, hydrogen really doesn't belong over there. In many ways, he belongs over here next to helium, and so that would put him to the right of oxygen. And then you're like, well, yeah, but we put him in the middle. So this is one of those things where we can't give you an easy rule for how to order those. I'm not going to mark it wrong if you order them incorrectly, okay? And I won't try to trick you in an exam. Just looking at the question, though, and going in the order that they were given is an excellent idea, because that is a suggestion, and that is the order that we put them in. Any other questions? Yes?
Would that affect the final answer?
No. Putting them in a different order would not. You might come up with C2OH4. And that would look funny to me, but I would know what you mean. Or OH4C2. Yeah. And this particular compound, there's actually more than one compound with that formula, might be written in different ways. So just, to throw that out there. But I just want the subscript with the correct element symbol. Any other questions?